Hello, this is Harrison Newman, and today we're talking about the Sun. The Sun has a luminosity of 3.83 times 10 to the 26 watts, and watts are the same as joules per second. It will produce this energy for around 10 billion years. If we want to know how much energy that the Sun will produce over the course of the entire 10 billion years, all we have to do is multiply our luminosity, 3.83 times 10 to the 26 joules per second, by the number of seconds in a year. After you do the calculation, we get that the amount of energy produced by the Sun in 10 billion years is about 1.21 times 10 to the 44 joules. How does the Sun produce this much energy? It is a complex process that requires an extraordinary amount of matter, which can be found as nebulous clouds in space that collapse on themselves as a result of the gravitational force and turbulence within the cloud. This collapse forces the gases into a state of high pressure, and due to the tremendous sizes of stars, this pressure is extreme enough to turn the gas into a plasma. Due to the high temperature and pressure in this system, a few protons will eventually be able to stick to each other due to the strong force. Typically, these protons will repel each other due to the electromagnetic force, but because of the high temperature, some of the protons are able to be accelerated to a very high velocity, which means that even though the hydrogen would typically be repelled if it got too close to another hydrogen atom, they will be moving fast enough that this force is overcome. Then there's a second factor, which is quantum mechanical tunneling, which is the result of quantum mechanical particles being able to effectively undercut the potential energy barrier that would stop them from going into a forbidden region. To understand how the electromagnetic and the strong force interact with each other, we have to look at a graph of the potential energy. At a very small radii, less than 1 femtometer, we have a very large negative number for our potential energy. That means that the two particles are going to be very strongly attracted to each other. Now at 1 femtometer or around 1 femtometer, we get a very high positive potential energy. This means that the particles are going to be repelling from each other, and this is why it's called the Coulomb barrier, because essentially for two particles to be able to stick to each other or undergo fusion, they have to be able to overcome this potential energy barrier, which is something that can only occur when the kinetic energy of the two particles is very high. That is why it is important for a star the temperature is very high for fusion to occur, or else it would just never happen. Another thing that's important to note is that in quantum mechanical systems there is a possibility for tunneling. That's why the line is cut short of the potential energy barrier, because even though the particles should classically not have the energy to overcome this potential energy barrier, they'll just do it anyways. And that's something that is very much based on probability. Here there's r min, and r min is simply the typical radius where things are repelled by the Coulomb force. One theory of how fusion occurs in the Sun is the proton-proton chain. First, two protons interact to form a hydrogen nucleus, which is one proton and one neutron. This also produces a positron and an electron neutrino. This is a result of beta plus decay occurring. Beta plus decay is when one proton turns into one neutron plus one electron plus one neutrino. Beta plus decay is also a result of the weak force. And now that we've gone through the gravitational force, the electromagnetic force, the strong force, and now the weak force, we have gone through all four forces in order to create a star. Next, once we'll have our hydrogen nucleus, it'll interact with a proton to form a helium nucleus. This helium nucleus is a bit unstable as it only has two protons and one neutron. This also typically produces a gamma ray, which will interact with another proton or another helium somewhere and will cause it to get a little bit faster. Lastly, our newly produced helium nuclei will interact with each other to form a more stable helium nuclei with two protons and two neutrons. This helium nuclei is also effectively the same thing as an alpha particle. This reaction also has a byproduct of producing two more protons, and these two protons will probably fly off somewhere to interact with something else as well. A nice way to sum up this reaction is that 4 protons and 2 electrons will form one alpha particle and 2 neutrinos. This also produces 26.7 mega electron volts. If we convert this to joules, we get that 26.7 mega electron volts is equal to 4.28 times 10 to the negative 12 joules. To figure out the number of times the Sun needs to do this single reaction in 10 billion years to produce the amount of energy it does, is we take 1.21 times 10 to the 44 joules, which is the amount of joules produced in 10 billion years, and divide it by 4.28 times 10 to the negative 12 joules, because this is the amount of energy produced by one reaction. This gives us 2.83 times 10 to the 55 reactions. For each reaction, we need 4 protons, so we multiply the number of reactions by 4 to get 1.132 times 10 to the 56 protons. To find the mass of protons needed is calculated as follows. We take our 1.132 times 10 to the 56 protons, multiply it by the mass of a proton, which is 1.67262 times 10 to the negative 27 kilograms, and we get 1.89 times 10 to the 29 kilograms. To put this in perspective, that's 31,600 times the mass of Earth. When all of the protons run out, it is typical for the helium to start interacting with each other and fusing through a process called the triple alpha process. First, our 2 alpha particles will interact to form a beryllium nucleus. This is typically very unstable. It has 4 protons and 4 neutrons, but no electrons, and it will typically decay back into 2 alpha particles. It even takes a little bit of energy away from the system to even do this. But if we don't have any hydrogen and there's a lot of alpha particles floating around, it's common for one of these beryllium to then interact with another alpha particle. This creates a carbon nucleus, which has 6 protons and 6 neutrons. This reaction also produces 2 gamma rays, which can release 7.367 megaelectron volts. This state of carbon is a highly excited state called the Hoyle state, and once in every 2,421 times, this state of carbon will spontaneously turn into the more stable form of carbon that is able to just exist anywhere with 6 electrons. If the sun continues producing 3.83 times 10 to the 26 joules per second, even after it runs out of hydrogen, how much helium must react per second? To sum the triple alpha process, 3 alpha particles react to form 1 carbon nucleus plus 2 gamma rays with 7.162 megaelectron volts. We again convert 7.162 megaelectron volts into 1.147 times 10 to the negative 12 joules and solve for the number of reactions per second. We take 3.83 times 10 to the 26 joules per second, or our luminosity, and we divide it by 1.147 times 10 to the negative 12 joules, and we get that it is 3.34 times 10 to the 38th hertz, or reactions per second. Since it takes 3 alpha particles for this to occur, we multiply that frequency by 3, and we get 1.002 times 10 to the 39 helium per second. Recall that we have 2.83 times 10 to the 55 reactions that produce 1 alpha particle each. We take our 2.83 times 10 to the 55 helium, divide it by 1.002 times 10 to the 39 helium per second, and what we get is that it'll take 2.82 times 10 to the 16 seconds. In years, it is 8.94 times 10 to the 8th, or almost 900 million years before the alpha particles will run out.